Hello, everyone. We are now at lecture 4.1. This lecture is about multimodal representation. Should be a fun lecture. So let's start with some administrative things. Usual reminder, I will probably put it in every lectures just to remind you. If you have any question, log in right now on Piazzal and click on, or you should see live Q&A, and I will allow you to see and post questions. At the end of the lecture, I will take the time to also go on all of these questions and answer or follow up on any of them if there is any need to follow up. So TA is also live chatting and answering. So this is great. We have pre-proposals completed, and all students managed to find teammates. So that's very exciting. The list of topics is great, and we assign and match all of your projects to a TA, and they should have contacted you already through Piazza. So just double check your emails. You should have received through Piazza a message from your primary TA. Your primary TA is the person to contact with any questions, primarily about the course project, but also anything else. They are there for you. They are there to help you. We don't have official office hours because we found that this idea of primary TA with who you meet regularly through the semester to work really well in answering all your questions. So as any time, if you would like an extra meeting, I'm always happy. And we'll have, in fact, not this coming week, not this week, not the next one, but on week 6, we will have, there's no lectures those 2 Tuesday and Thursday, on purpose to give you more time to work on the first project assignment. But also, I will use these times as some virtual office hours as well. So, so the first project assignment is coming in a little bit more than 2 weeks. So it's good to start working now. Don't wait. I've always told you, like, don't wait 2 days before the deadline. This is not the type of project report you want to wait 2 days before. The project report has 3 main parts. The first one will be relatively easy. This is a restatement of the introduction and the experimental setup you're planning for the project. This will be probably some extension and rewriting on the pre-proposal, but in the same vein. One part that will require time, but it's good to do it before and not after the project, is the idea of studying related work. And we want you to cite 12 to 15, a minimum of 12 papers in your related work section. 3 or 4 of these should be like the most related to your work, and these you should even like give a little bit more details about these, not to the point of writing equation, but at least writing 2 or 3 sentences about these most relevant and how they compare with your proposed work. And then the core is one of the main core is the new research ideas. And don't worry, at this point, this is still early in the project. You may have some ideas, not completely sure about it. Don't worry, just write them down. This is the goal is to give you feedback. In fact, this coming week, you should be meeting with your TA, primary TA, to discuss those research ideas. And as you start working with the data, you will probably realize that how to tweak or change these ideas. So part 2 is about sharing your research ideas. A rule of thumb, if you have a team of 4, I'm kind of expecting about 3 ideas in this. If you have a team of 5, 4 ideas, that's 1 less as the number of teammates. Part number 3 is where you will have the most coding to be done. And the goal is threefold. One is to just get yourself used to and also start understanding your data set. So each data set has its own particularities, so it's really important for that. The main two goals of part 3 is to look at language in itself. These are unimodal explorations, and try to find how is language related to your task. What is the type of structure you see in your language? And so the simplest one, which is the one we suggest in the instructions, is to just look at lexical representation and semantic representation and see how these relate to your labels, to your class, to your task. You should try to qualitatively visualize these. This is really an exploration. This is qualitative, but also to try to understand, like, are they in my big data set? Are they some, let's say you do instruction following. Are they different kind of verbs that are used in my following instructions? And it's probably useful for me to know what is that, all these type of words, because some words, some verbs may be very easy to replicate with an AI system, and some other verbs may be much harder. And so qualitatively understanding that is important, but also using some embeddings, we already talked about Word2Vec, and we'll talk about other ones next week. The goal is to explore the data and also explore the tools, understand the tools themselves. So language exploration, and for visual, you expect you to use CNN and at least run a CNN on your data, or at least on a subset of your data. If your data set is too big, takes too long to run, it's okay to do it on a subset. But we want you to understand, like, you have all these images. Let's say also it's about following instructions in like room to room or some other data set like it. We want to see what are those images, what are the objects that are seen there, how is CNN picking up on these objects, how are these maybe object related to your task. Let's say the task is turn left, like can you see some relationship or picking up objects, specifically like verbs. So we want to do the visual and the language. These explorations, we on purpose ask you to do them on your own data set, which also means that the instructions are a little bit vague, because it's very hard to create one set of instruction for this part 3 that works for all possible data sets that you guys are working on, which can be quite different from each other. So for that reason, we decided to leave it a little bit qualitative, a little bit general in the instruction, and you work with your TAs to confirm if they are correct, or how to explore for your specific data set. So talk with your TA about this. The part that is going to be really interesting this year, because this is the first time we will do it remotely. Usually the proposal presentation were in person. This time we will do them remotely. So what it means is that you are recording, you're making a recording of your presentation. And in this recording, you only focus on the research ideas. Like, don't focus on the unimodal exploration or on the visual exploration, or you could discuss very quickly related work, but the core of that presentation is to explain your research ideas. And the reason for that is that we have a second part, which you could say almost as a third part, like report, proposal, presentation. And then the last part will be peer feedback from other students. And so for the purpose of presentation, focus only or primarily on the research ideas you have, because the feedback, you want to get feedback about it. And we will have students watching, your peer student watching it and giving feedback. When you submit, you need to submit two things: your video recording, MP4, and there's a link. It's in the instructions also, which are the instructions for the presentation are now online on Piazza. And you need to submit a PDF version of your slides, and they need to match to each other. Like, don't try to submit your MP4 and then changing it or vice versa. They need to match with each other. The deadline for it is Friday, in 16 or 17 days from now. So you see, you need to start thinking about it. The deadline for the report is the Sunday right after. So Friday is the presentation, and Sunday the 11th is the report due. We give you 2 more days to finish the report. We want the proposal presentation earlier because we need to prepare for the peer feedback. So all the videos, because they're submitted on Box, we will put links to this on one big post. We have 24 projects, so all 24 projects with their videos will be there. And we will also have 24 posts, separate posts, one for each project. And the reason is to be able to submit your feedback to the team. So any feedback you want to post on a specific project, you will have a post associated with each of them. And your goal is to watch at least 6 of them. We'll give details about the matching, how to match you with the other projects. But yeah, on the 6 videos, you should watch. And for them, for these 6, there's a minimum of 6. You're very welcome to comment on a lot more. All 24 of them, like we are planning to do. But you also like leave a decent, like at least 120 words feedback about it, about the ideas, maybe pointers you found, that the kind of follow-up you could or alternative they could explore. And these feedback is the following Friday. So we have 1 whole week. It may take us a day max to put everything together. We'll do it as fast as possible. And then you have another 5 or 6 days to share the feedback. So this is the main thing. If you have questions about it on Piazza, we'll answer anything, or at the end of this lecture, I will be happy to answer them. Today, our presentation is about multimodal representation. The focus today is primarily about these multimodal representation, coordinated joint representations. But I will also, before that, discuss for a little moment about graph-based representation. And I'm presenting this because this was discussed a few times in the comments from lecture 2.1 and some follow-up comments afterwards. People were asking about graph-based representations. And given that, I'm happy to give a little bit more details on this, also some pointers for people who are interested to read more. So I want to share that knowledge is one of these things we will want to represent in a graph. So last week it was language, vision, and now I just want to present graph representation. And there's this great tutorial from Professor Leskovec from Stanford on this topic, which I invite you to look at. So we, last week, at the end of last lecture, Thursday, we discussed tree-based RNN or recursive RNN. And the idea here was to be able to represent or take advantage of a tree structure like a parsing tree and use this in a LSTM type recursive network or recurrent neural network. And the big change here was the idea that instead of modeling this this type of sentences as a sequence, we take advantage of the parsing information and use this to aggregate the information. So we use this parsing information to change, instead of using it and simply doing a sequence, which is the typical LSTM. Here we will aggregate information in a way that takes advantage of parsing. Now, this is great when you have a tree-based parsing, but in many cases, the information is not through a tree and can be a lot more unstructured. And how can we take advantage of that not completely unstructured, but that structure can be a lot more flexible. And the term, just terminology, some people call them graphs. There's also networks. I will sometimes mix that. I will use one and the others. the graphs or networks, I will use both the terminology. So social network, Facebook or Twitter, these social networks are very large-scale version of a graph where every node is a person. You also have an economic view, or also in a company, when you have a company and all the workers, how they interact with each other. You have it from a knowledge base or from the web, how the web page are related to each other, or the brain, how the brain neurons are related to each other. These are all examples where a representation of a graph will be a great way to move and to represent information. And when you have a graph like this, there are many tasks that could be done. One of them is clustering, and I will talk about this kind of unsupervised approaches or similarity-based approaches. But another one will be about a supervised task. An example, if you have online social network and you would like to detect which of these actors or these people on the social network are human and which one are in fact just a bot, you could expand to that to be looking at topics. Or so the goal is to be able to from your network, be able to label an associated subset of nodes. Now, it could be a subset of nodes, and because you already have some of the labels, or it could be all nodes. Both tasks can be explored. There is quite a few cases where you already have some, and you'd like to kind of propagate the labels to other in here. So that's also a very interesting aspect of this. So this is one way a graph can be used, and in this case is a supervised task, and this is the one type of learning you'd like to do. Another one, which is closer to unsupervised task, is to take advantage of this structure, and so the structure may be defined because of like friends, or it could be defined because there is a web page linked to another. And the goal may be to learn in that kind of unsupervised, or the only supervision you will have is the links. So either you call it completely unsupervised or you call it weakly supervised, but the only information you will have are those links, but no labels. And our goal will be to learn a similarity and learn an embedding in such a way that in this embedding space, two nodes that are connected, that are similar, and the similarity could be just like, is it connected or not, like 0 or 1, or you could have it sometime have a weight associated with it, how connected or close they are. And you want to use this and be sure that in that embedding space, this is a constant in the sense that two things that are connected will also be very close in the embedding space. And you could imagine on top of that, having some kind of clustering on top of that as well. So this is more of an unsupervised task. And this is, I will say, a little bit of a classic approach. Many of the network-based will often explore these clustering, trying to understand the data. Let me formalize a little bit graph neural network, or just at the basic, a graph in itself. A graph is a series of vertices or nodes. You can call them nodes or vertices. And then you have edges, connections between them. And often these edges can be represented by something like an adjacency matrix. Adjacency matrix could be just binary in the sense that 0 or 1 if this is connected, or 0 otherwise. So this is the basic of a graph. In the case of a graph neural network, often you will associate with each of these vertex or these nodes. You may associate also some descriptors for these. It could be categorical. You could have like attributes like age or gender, or you could have some text associated with them, images. There's a lot of very interesting information, and that's probably closer to what we do. And what you see here that's very interesting is that this data could be multimodal. In fact, there are some very interesting work where maybe some of your nodes have text and some of your nodes have images and some of your nodes. So it could be that your network is in fact multimodal in the sense that or it could be multimodal in the sense that every nodes have all these different type of information. All of the above is really interesting. One thing that is optional, and mostly in the case of the supervised, is that you may have associated either just during training or maybe also at test time nodes and labels for these different nodes. As I mentioned, this is optional. If you do the unsupervised, it's not required. So this is the formulation, and so there are quite a few approaches, but a lot of them uses similar ideas, and this is a nice intuition, and that's a little bit the similar intuition that we had in the tree RNN. And the idea here is that if I want to model the graph, it can be a very complex graph. And so how can I take this graph and make it into a neural network? The first key intuition is to look at neighbors. So I will look at it. It's has almost the same kind of intuition as Monte Carlo, like MCMC, like a little bit. But that intuition, a lot of these Markov assumptions of looking with your click and looking like this is a little bit of a similar for people who work on this topic. But yeah, the intuition here is locally the information. What is connected with A, for example? It's D, B, and C. And so as at the first level, these three are the most relevant with A, and this is where I get most of my information. Now, in practice, like B can also be connected with C, but C is also connected with F and E. So A indirectly should have a connection with F and E. So, but at the first level, we want to have it local. So if I have a target like A, we are at the first level, we'll say, hey, what really connects, or what the knowledge, what is the messages I want to get, or what is the relationship, is my neighbors and myself, maybe myself and the neighbors. These are really what is really key into that. But we'll make it a multi-layer and in kind of a recursive manner. Going from A, I can say from B, what is related to B? And it's A and C. And that's what you see here. And from C, what is related? It's A, B, C, E, and F. And what is related to D? Only A. And so now you can see, and you can see that recursive going on. And what will allow us is that like a relation between C and A will still be modeled just after 2 layers of neurons. And in fact, these will be in fact neural networks. That's where, or at least in recent works, has been used as an aggregators and learning how to aggregate this information. One thing that's important to realize is that this kind of network is created based on the input graph. You create these networks, and for each target node, you get a different of these graphs. That's really interesting. So this input graph gives us those 6 different graphs. And here we're only showing 2 layers, okay? And I'm writing it again. So the same graphs here, I'm writing them again here. And so here we have multiple layers. We have the original input. We have a first layer. We have a second layer. And there's nothing that stops us from doing a lot more layers. Almost nothing that stops us. I will tell you more in a second. But in general, in theory, you could go as far as you want. The one issue that we'll discuss is the same that we had in other neural network. If you add many layers, what is the issue? Vanishing gradient. So the same issue will happen also here. But in general, in a graph neural network, this is an example of a graph neural network. And what's very interesting here is the idea of local. That's the first take home, and the idea of multiple layers. These are some of the take home. And another take home, as many of the neural network and that we've seen, is that all of the module, all those aggregation modules here will all share the same parameters. All of them here at layer 2 will share. And by default, usually in the basic graph neural net, the parameters will only be shared by layers and will not be shared between layers. And in a multi-layer perceptron, you kind of see a little bit the same thing. Between layer, you get new neural. But the tying of the weights, in a little bit like the RNN will do there. So how do you use that kind of architecture? Up to now, the only thing I got is some kind of embedding. Here I get my input X, and here what I have is my output are just Z, like some kind of new embedding for A. But how do I make this kind of output Z of A and use it for supervised? Then I can use probably any loss. I'm just putting one of them here. And there in this loss, I can take this embedding and look at how closely it relates with the label and giving the classification weight. Classification weights are whatever weights that are in my neurons on all of layer 1 and layer 2. So here I'm only putting it as if it was a one layer, but in practice, this could be for any as many layer as I want. So this is only for binary, human or not, but this could be also multi-class as we've seen. So this is for supervised learning. There are one questions that, and if you were to do unsupervised, I didn't put a slide for it, but there are some very well established algorithms that you can do to also study how to learn and put some kind of supervision on the Z so that eventually you keep the similarity as close to each other. And there's quite a few of these, Node2Vec being one of them, for example. But yeah, one of the questions is, how do you aggregate all of these together? And one of the issues is that sometimes I have 3 inputs, sometimes I have only 1 input, sometimes I have 4 inputs. So how do I aggregate multiple of these? How can I handle multiple? And probably the first thing that comes to mind is average pooling. I can end up just averaging. Here what I have is I take all of my H here and I just average them, and then I just multiply by my W, and here I just made the W. I didn't put the bias here. And one thing also is to be remembering is that you should also have probably with yourself, you should probably remember the previous how was A at the previous layer? How was A before I make this aggregation? So you want to keep some consistency here. And so these different, one thing that is the average pooling, at least the one that was originally proposed, was that the way you aggregate all of your neighbors will have different weights than the way you process your own representation from the previous iteration or the previous layer. One extension which got a lot of interest in the AI community is the graph convolutional network. It's a small change from the more typical average pooling, where in fact you end up treating yourself, the self node, you end up treating it with the same weights. So you don't learn a different W or BK, but in fact use the same. And one other thing, and what's nice by doing that is that suddenly things are going to become a lot more efficient. So every node can efficiently be processed because there's the same set of weights for every node, whether it's myself or another. And by adding a simple different normalization, that's one small change that they did in the graph count. But the bigger change was probably this change of weight, because that changed also the efficiency of the algorithm. But one of the issue, like average pooling and graph convolution networks, is that naturally, by default, they will have a harder time with very complex and multiple layers. They will have the same issue that we've seen in some basic RNN. And for that reason, people have looked at extension. And one of the interesting one was, which is probably makes sense, the same way RNN, if you want to help with the vanishing gradient, then you can use an LSTM or a GRU. I didn't discuss in this case in details the GRU. GRU can be seen as a somewhat of a simplification of an LSTM, but the goal is the same, is to help with the vanishing gradient. And so the GRU is going to be the same GRU formulation as in a recurrent neural network, but here we're going to use the GRU over layers. Because where's the problem with vanishing gradient? The vanishing gradient is not from left to right, it's from up to down, it's from between layers. And so the GRU is going to be helpful between layers, and that will be how we will be using it. So same weights also across layers. So suddenly what is nice is that you're also going to have in this architecture the same weight, because if you make it a recurrent process over layers, then suddenly the same set of weight at layer 1, at layer 2. And so that will allow, because of the GRU, will allow to do a deeper project, so a deeper network. So there's some citations here, some of the like landmark work in this, and there's been some extension. One that I didn't have time to talk about, but that is quite interesting, is called subgraph embedding. So the same way we in the language, we look at word-based embedding. So you have a sentence and you look at embedding each word. But what if I wanted to embed a sentence in a graph? Like in a graph, I want to embed a subgraph. Like there's a big graph and there's a sub part of the graph, and I'd like to have one embedding for the whole graph. Hey, you can probably see the same intuition as we had with sentence embedding. And so that's a really nice and interesting aspect that is, and it's still an open question on that. So great. So I wanted to talk about these graph-based embedding, but the main focus today will be on multimodal representations. What do we want with multimodal representation? Our goal, what are our goals when learning these multimodal representation? At the first level, we want to identify similarity in that space. We want the same way, in a sense, as we just talked about embedding in the graph, but this is true with multimodal entities that, or concepts that are similar or equivalent in different modalities. They should, in that representation, they should both be similar as well. We want probably also this representation to be useful for prediction tasks like retrieval, mapping, and fusion. So the representation could be learned unsupervised, but also, but we want to hopefully be useful for another prediction task, or I say prediction task here in the figure, but it could be also for other analysis as well, like clustering as well. We want it to possible to obtain in absence of modalities. That's one thing that we didn't discuss as much here, but sometime with specifically with joint representation, what is one of the advantages you may want is that this representation should be, we should be able to use it even if we have a subset of representation. And sometimes you want it to also feel missing modality the other. So maybe even though the modality 2 is not present, you may be able to use that multimodal representation in some kind of translation perspective. So these are different applications or different ways to use representation, multimodal representation. I just bring back the core challenges that I discussed about 2 weeks ago on multimodal representation. One way of learning representation is joint representation, and that is one of the core aspects of today, what we'll discuss. Joint representation is this idea where everything goes, all modalities will end up in that same space, and things that are similar to each other will be close to each other. But as I hinted at already, and we'll discuss more on Thursday, there's another field, a subfield of coordinated representation. I will say it's also probably the one that has been the least explored, and I think very interesting aspect. And so in the coordinated representation, instead of pushing everything together in the joint space, you will say, hey, I will have a separate space for my two modalities, but I will find a way, I will force some aspect of each spaces to be coordinated with each other. It could be some elements in the two modalities that are similar to each other, and I want these to be close. I could also make it so that there's another way to translate from one to another modality, so that the coordination could be, it's kind of a spectrum from very weak coordination. The weakest of it is to have two separate spaces that are not connected to any kind of coordination. And then you have the strongest, which in fact end up being joint representation. So you have this this representation. We have, I want to discuss, when you learn these representation, the idea of learning unsupervised, and we hinted at this also when I talk about the graph-based representation. And at the basic, like just from a notation perspective, the idea is you have data but no label. And why would you want to tackle is to often unsupervised learning allows us to do some analysis about in the data by looking at the similarity and clustering, that we can learn from that. We can find, for example, the famous topic modeling. Sometimes it's helpful also for data compression, looking at trend. And often, in the case of neural network, it may be seen almost as a pre-training to use a lot of data to learn a better representation that could maybe use better later for supervised tasks. So unsupervised representation, it's to force a representation to better model the input, not just extracting the feature for classification, asking the model to better represent the data. This is more about representation learning in general. And so for students who read the paper on representation learning, you've seen that, and hopefully everyone through the discussion also picked up on all these main points. And this unsupervised will also hopefully help with generalization. And as I mentioned, it's a lot of time can be used for initialization. So the simpler the representation learning, and I reduced a little bit the number of slides on this. I think it's a very cool algorithm, and we'll discuss a little bit more when we talk about probabilistic graphical model. But RBM, restricted Boltzmann machines, were some of the most, some of the original multimodal, I will say two of the landmark papers. One was using autoencoder, the deep multimodal learning, multimodal deep learning, but there was also very soon after and one on RBM. The RBM being nice because it was a generative model. So this one could really be learned really just from the input. So from the input, you concatenate your input, and then you through the RBM algorithm will learn a representation. Usually that shared representation will be a little bit smaller to force some kind of aggregation of the data. But although RBM are great and conceptually are very interesting, in practice there are a lot of challenges in optimizing them. And so although both came at the same time, definitely one of the two really took over the other very quickly. And the autoencoder is the one that really came out stronger of the two.